In this lesson, we will talk about one of the most famous and fundamental algorithms in computer science, binary search. We find the application of binary search in a large number of problems, in a large variety of problems in computer science, but here let's try to learn it in its simplest form. And to do so, we will define a problem first. And the problem is, given a sorted array of integers, a sorted array means that the elements in the array are arranged either in increasing order or in decreasing order. Like in this array here, the elements are arranged in increasing order. Let's say the name of this array is A. The size of this array is 9, so we have index starting 0 till 8. Now, given such an array and a number or an integer x, we want to find out whether x exists in this array or not. And if x exists in this array, then we want to find out the position at which x exists in this array. So for example, if x is 81, does 81 exist in the array? Yes, 81 exists in the array A and it exists at index 7. Does 25 exist in the array? No, 25 does not exist in the array. Does 21 exist in the array? Yes, 21 exists in the array at position 3, at index 3. Now, what would be the logic to find out whether x exists in this array or not? One simplest approach can be that we can scan the whole array to find out the desired number. So we start at index 0 and compare this element with x. If it is equal to x, then we are done with our search. We have found the element in the array. If not, we go to the next element. And we keep on comparing with the next element until either we are finished with the array or we find the number. So let's say if we wanted to find 63 in this array, then our search will be over when we reach index 6. We start at index 0 and our search will be over at index 6. If we wanted to find out 25, our search will be over at index 8 with the conclusion that 25 does not exist in the array. This approach will work irrespective of whether the array is sorted or not. And if I have to write a code for this, it will be pretty straightforward. Let's say I want to write a method search that takes an array A, its size n, and the number x to be searched for. And the code would be, we will run a loop starting 0 till n minus 1. So for I starting 0 to n minus 1, if the element at index I is equal to x, then we return I, which means returning the position at which we have found the element x, and our search will be over. And if we cannot find any such I, then we return minus 1. Let's say returning minus 1 means that we could not find the element, we could not find x in the array A. Now with this algorithm, if we are lucky, we will find x at first position itself. So in the best case, we will make only one comparison and we will be able to find the result. In the worst case, when x would not even be present in the array, we will scan the whole array, we will make n comparisons with all the elements in the array, and then we will be able to give back a result that, hey, x does not exist in the array. So the time taken in the worst case is definitely proportional to the input size of the array, or in other words, we say that this would be big O of n in terms of time complexity. It's always good to analyze the running time of an algorithm in the worst case and find out the upper bound of the time taken. Now in this case, the time taken grows as a linear function of n. So we also call this search linear search. And once again, if we are using linear search, we are not using any property like the array is sorted or not. Whether the array is sorted or not, this will work. Now let us try to improve this algorithm using the extra property of the array that it is sorted. And I will make some space here first. Let us say we want to find out whether number 13 exists in the array A. So x is 13 and we want to find out whether x exists in the array A. Now we will use a different approach this time. Instead of comparing x with the first element, as we do in the case of linear search, we will compare it with the middle element in the array. Now the size of this array is 9, so the middle element will be at index 4. Now there can be three cases here. Case 1 can be that x is equal to the middle element. If x is equal to the middle element, we have already found x in the array. Case 2 can be when x is less than the middle element. And case 3 can be that x is greater than the middle element. Clearly, if x is equal to the middle element, our search is over because we have found x in the array. If x is less than the middle element, then because the array is sorted, it lies before the middle element, and we can discard the middle element and all the elements after middle element. Similarly, if x is greater than the middle element, it lies after the middle element, so we can discard all the elements before the middle element and of course the middle element as well. So in case 2 and 3, we discard half the elements from our search space and reduce our search space. So in this example, when x is 13, initially our search space is the whole array. X can exist anywhere in the array. Now we compare it with the middle element, which is 36. Now x is less than 36, so it should exist somewhere before 36. So we discard all the elements after 36 and 36 as well. So now the problem gets redefined. We need to search x only between index 0 to 3. So how do we keep track of the search space? We keep track of the search space using two indices, start and end. So initially the start would be 0 and end would be the last element in the array, in this case the index 8, because initially the whole array is our search space, and we calculate mid as start plus end upon 2. Now once we find out our reduced search space, we adjust start and end accordingly. So in this case, after comparing 13 with 36 and discarding half of the array, our end now becomes index 3, which is nothing but 1 less than the middle element. Now we again find out the middle element in this reduced search space. So here the middle element will be 3 plus 0 by 2. If we take only the integral part, 3 plus 0 by 2 would be 1.5, and if we take the integral part, the middle element would be index 1. Once again, is it equal to x? No, 6 is not equal to 13. Is x less than the middle element? Is it case 2? No, it is not. X is greater than the middle element. So this time we discard the middle element and all the elements towards its left. And this time we shift start to mark our new search space. Now the new search space is starting at index 2 and ending at index 3. Now what is the middle element? 3 plus 2 is 5, 5 by 2 is 2.5, and the integral part is 2. So this is our middle element. So x is now equal to middle element. We have found our element. So we are done with our search. This kind of search, where we reduce the search space into half at each comparison, is called binary search. Once again, we are able to reduce the search space by 2, or in other words, we are able to reduce the search space into half only because the array is sorted. Array being sorted is a precondition for binary search. Okay, so let us now write code for this algorithm. I will write a method binary search that will take as argument an array A, its size n, and a number x to be searched for in the array. And I will initialize two variables, start to 0 and end to n minus 1. So start and end define our search space. Initially the whole array is the search space. Now I will write a condition here while start is less than or equal to end, and I'll come back to why I'm writing this condition. So while this is true, start is less than or equal to end, we will find out the middle index of the search space as start plus end upon 2. And now we will write three cases. If the middle element is equal to x, then our search is over. We return the index stored in the variable mid and exit from the function. If x is less than the middle element, then we need to discard all the elements having index greater than or equal to mid So our end of the search space now becomes mid minus 1. And in the third condition, which will be x greater than the middle element, which will be the default condition after these two if and else if, we need to discard all the elements with index less than or equal to mid. So our start becomes mid plus 1. And if we exit this while loop without returning anything, then we return minus 1, which will mean that we were not able to find the element x in the array. Now why this while statement here with a condition start less than or equal to end? What we are basically doing in our algorithm is that we are reducing our search space recursively by adjusting the start and the end pointer. Now there must be an exit condition to our recursion. The exit condition can be either we find the element in the array, so we return and exit, or we exhaust the whole search space. When start is equal to end or start is less than end, then we still have search space. When start is equal to end, then our search space has only one element. So when this condition becomes false, we have exhausted our search space. We need to exit the loop and we need to return minus 1 to tell that the element the number x does not exist in the array. Now once again, in this case, in the best case, we can find the element x in just one comparison when the first middle element itself will be the element x. In the worst case, we will keep reducing the search space till the search space becomes one element. So from n we reduce to n by 2, and from n by 2 we reduce to n by 4, and we go on till our search space becomes 1. Now how many steps does it take? Let's do some maths here. Let's say it takes k steps to reduce n to 1 by dividing by 2 at each step. So n by 2 upon k will be equal to 1. And if you solve this, then k will be equal to log of n. The base will be 2. So in the worst case, binary search will take log n comparisons, and so the time taken also in the worst case is proportional to log n, or in other words, it is big O of log n in terms of time complexity. And big O of log n is a lot more efficient than ON algorithm. So this was binary search. We will take more problems on binary search in the coming lessons. Thanks for watching.